We have been discussing about total quality management. In the previous lecture, I discussed about the contributions of various quality gurus, Dr. Deming and others. It was also told that these quality gurus emphasize the importance of statistics in total quality management. So today, I will devote this lecture for telling you about the application of statistics in TQM. We will discuss some very basic things about statistics. So, in statistics, we need data. Now, data is basically any measurement or observation. It can be numbers, but in fact nowadays we can have data in the form of figures, etc. also. Big data analytics is very hot topic nowadays. Now, presentation of data can be done by various ways. We have frequency diagram, we have bar chart, we have pie diagram, we have frequency graph, line diagram, frequency curve. All these things you must be familiar. You can revise it again from particular books. Say for example, this one is a type of pie chart. We are showing that US federal spending, and like in healthcare, it is shown that 25% amount goes social security, 24%, like that in the form of pie, that means sector of the circle we have made it. Then similarly we can have bar chart, like here machining environment dry, then at 90 rpm what is tool temperature, at another rpm what is tool temperature, like that we make. So what are the type of statistics? One is that called descriptive one, other is called inferential. Examples of descriptive statistics means just giving the description of something, like we say average rainfall in Shillong last year. This is just a information. So for that purpose also statistics is used. Number of new phone connections in 2003. This is also just a information. You need data. That is what that descriptive one. And inferential statistics is that when we make some inference about something, we make some forecast, we make some interpretation, like that. So first about descriptive things little bit we will tell. So statistics is actually a discipline in which we study all these things, that it is basically type of data science, but also word statistics is used basically in another sense also. That means, you know, particular information about the data arranged in proper way. So now statistics is a set of methods, mathematical procedures for organizing, summarizing, presenting and interpreting information. So this is about discipline, that you know statistics discipline means it will provide you a set of methods, mathematical procedures for organizing, summarizing, presenting and interpreting information. Interpreting information falls in the category of inferential statistics. Presenting etc. is part of descriptive statistics. It helps bring order out of chaos, because otherwise you have a lot of data, but if you, who will remember that so many things? So therefore it is better to find out some way. Say for example, you have data about the weight of students, then you take the average, you take the standard deviation, and in that form when you present, then it becomes little bit more manageable. So that is why it is said that it helps bring order out of chaos. It provides standardized techniques for communicating and interpreting information, then vocabulary and symbol for communicating about data, and it also gives a theory about decision making. That is the part of inferential statistics. Tools that allow us to make judgment under uncertainty. In fact, probability is also a part of statistics. Okay, in that we discuss that probability theory can be taught separately also, but it is also a part of statistics, particularly we talk about statistical probability. Okay, if you are talking about empirical probability, then that can be different. Okay, so now I am going to tell that what do we mean by population and what we mean by sample. So population is a set of all individuals of interest in a study. Suppose you want to find out the weight of all the people in a city. So all the people in a city, they form population. But the sample is a set of all individuals selected from a population, because we cannot take the weight of all the persons in a city, it will be very expensive. So we make the random sample, maybe we measure the weight of 100 random people and then make some inference. So then it becomes a sample. Even when we go to a doctor's place and he wants to check that what is the condition of your blood, so he will recommend not that whole blood should be checked, but a sample is taken and that sample of the blood is checked. So sample is a set of all individuals selected from a population. It is intended to represent the population. It should be identified in terms of the population from which it was selected. So why not just collect data from the whole population? It is very obvious that we cannot do the measurement of whole population, because sometimes it is very impractical, often it is impossible, and usually it is unnecessary also, because we can get the information with a small sample. Then why measure the whole thing? Okay. So relationship between population and sample is shown here pictorially. Population is the all of the individuals of interest, maybe the people living in a town. Okay, all of them are individuals of interest. Then the sample is selected from this population. Then the sample means the individual selected to participate in the research study, and the results from the sample are generalized to the population, and then again we make some inference about population. So this type of thing goes. Now question is that about parameter versus statistics. Now here the statistic is used in a different sense. Parameter, when we say parameter, it is a value, usually numerical, that describes a population. Say for example, we can say average weight of or mean weight of a population. So it may be derived from a single measurement or a set of measurement from the population. Whereas statistic is a value, usually numerical, that describes a sample. So suppose sample mean, this is a type of statistic. So may be derived from a single measurement or a set of measurements from the sample. Each population parameter has a corresponding sample statistics. What is the population mean and what is the sample mean? So now we come to inferential statistics. It is tool for drawing inferences about a population from data collected from a sample. Example, we take the opinion poll of 1,000 Indians for knowing who will be the best prime minister. So we make inference about whole population's opinion, but it is based on only the opinion of 1,000 persons. Based on that we make the inference. Now sample which you take, that should be representative of the population. So a goal of inferential statistics is to generalize from samples of populations. Generalization will depend on how well the sample represents the population. Representative sample is a sample whose characteristics are similar to the population. So it should be very representative. It should not differ from the population. It should not happen that suppose you are taking the sample of people from a town and you take only people in the age range of 20 to 30, then it will not be representative. You have to take a random way so that people of all age group can come, like that. So main thing is that you have to do random sampling, random selection. It is process for obtaining a sample from population that requires that every individual in the population have the same chance of being selected for the sample. So it should be random. Then what do we talk about sampling distribution? Now consider a finite population of 4,000 students of a certain college. Of these 200 students are selected randomly and their mean weight is calculated. It was computed as x is equal to 61 kg. Suppose if we draw 20 different samples of 200 students, instead of just one as we did previously, we cannot expect the same mean weight of these 20 samples chosen randomly. It is due to sampling variability, that is, each sample drawn randomly from the same population differs from each other in their computed statistic. So the means computed is listed like that. Suppose you got this type of means. If one sample gave the mean as 59, other gave mean weight as 62, like that, and finally this one. So this can make a distribution type of thing. This is basically sampling distribution. So these are 20 values from what is known as part of the sampling distribution of a statistic mean weight. Therefore, the sampling distribution is the statistic calculated for a large number of random samples drawn from the same population. So it is basically distribution, and we can show in the form of a bar chart, etc. also. Alternatively, consider all possible samples of size n which can be drawn randomly from the same population, and for each one compute the aimed statistic. In this manner, we obtain the distribution of the statistic, which is the sampling distribution. Now we compute mean of this sampling distribution, which is 61.16 kg. Now recall the list of means computed for 20 random samples. We observe that the 20 sample means differed from the two population mean. Two population mean was 16.16 kg, but it differed. That means 62, 64, 63, like that, and they are clearly above the two mean, while 59, 59, 60, 60, like that, they are below the true mean. So these deviations or differences from true value is due to the variability of the samples. This is known as random error in statistical estimation. So there is random error. Note that the mean of 20 random sample means is slightly greater than the true population mean. So if we take 20 more samples of 200 students, the mean of this new sampling distribution might be lower than the true population mean. So there may be difference. So population mean, that is mean weight of 4,000 students, is 61.16 kg. Let us say in case of infinite population, this may not be known also that what is the mean weight, but suppose 4,000 students are there, you can do experiment and you can find out what is the mean weight. So therefore 61 kg is not a bad estimate of the population mean, but 61.15 kg is still better estimate, not LB but it is kg, is a better estimation because it will be close to that. So more the sample means, that is statistics is included in the sampling distribution, the more correct the chances of the mean of the sampling distribution becoming an estimate of the population mean. So if we take the more sample means, then we can get more correct estimate of the parameter. Now there may be some situation that sometimes other than random errors, error arises due to the tendency of consistent underestimating or overestimating a true value. This is known as systematic error or bias. So suppose in the example discussed, an investigator is investigating only those students who are healthy and fit, he would most likely overestimate the population mean. Generally, healthy bodies have reasonable weights. Clearly, the investigator's choice is one of bias, and it can be other way around. So this is an example from one of the bias that occurs in estimation. See, this is a true mean. Here there is a less variation and low bias is there because both the values are on both sides of the true mean. Means some values are underestimated, some are overestimated. But this is a true mean. Here also variation is less, but it is highly biased because all the sampling mean is actually showing the lower value. So it is one side of the mean. So therefore it is having bias. So about sampling error, there is generally some difference between a statistic, that is the value obtained from a sample, and its corresponding parameter of the population. In example discussed, the mean of the weights of 200 students taken first sample is slightly different from the mean of the weights of 4000 students, that is the population. This difference is called sampling error, whose type and situations are discussed. This error can be minimized by increasing the size of the sample and by taking samples of extremely random in nature. So we can reduce this error by increasing the size of the sample and also ensuring that the sample should be quite random. If the size of sample is large, the sampling error is small. The accuracy of the sample increases as the square root of the size n of the sample, that is according to under root n. So if you want to reduce the error by half amount, that means suppose earlier that error was something like 5% and you want to keep it 2.5%, then you have to make the sample size 4 times bigger, because it is reducing as per under root n rule. Hence we take samples of sufficiently large in size. This is very important, that the accuracy of the sample increases as the square root of the size n of the sample. Now there is one very important theorem in statistics, that is called central limit theorem. So what we have discussed with an example is stated as a theorem called central limit theorem. It states that when the size of the sample increases and becomes sufficiently large, the distribution of the sample means tends to normal distribution. That means even if we take some data from uniform distribution, but we make the sample means, these means will be distributed according to normal distribution or bell-shaped curve. Okay. So normal distribution curve, I think everybody knows that it is also called bell-shaped type of thing. That means more data will be concentrated in one position mean, and then gradually it will go like that. Okay. So this is this one. So this may be frequency and this may be suppose the mean. Okay. So you know that this type of normal distribution is there. In most of the cases in nature we get normal distribution. Suppose some worker is making some shaft and we have instructed him to make 50 mm diameter. So more or less that most of the shafts will be around 50 mm diameter, but you know that some will be oversized and some will be undersized, and deviation keeps, frequency of deviation keeps decreasing. As deviation increases, less chances are there that that type of thing will come. So here that central limit theorem is stating that when the size of the sample increases and becomes sufficiently large, the distribution of the sample means tends to normal distribution. Now here we must take one thing in our notice, that the theorem is equally valid for both normal and strongly non-normal. We restate the central limit theorem as even if the population distribution is strongly non-normal, its sampling distribution of means tends to normal distribution for large sample size. And we have seen that the sample mean is distributed normally with mean m, the mean of the population, which is an unbiased estimator. It can be shown that the standard deviation of the sample means called standard error is equal to sigma by under root n. So if sigma is the standard deviation of the population, then the standard error or standard deviation of the sample means is sigma by under root n. So as n increases, your deviation reduces. Okay, standard deviation reduces. Now we talk about that one thing, important point about hypothesis testing. Many times we strongly believe some results to be true, but after taking a sample we notice that one sample data doesn't fully support the result. The difference is due to the original belief being wrong and the sample being slightly one-sided. So this is the part of inferential statistics. You want to make inference about the hypothesis. So tests are therefore needed to distinguish between two possibilities. These two tests tell about the likely possibilities and reveal whether or not the difference can be due to chance elements. If the difference is not due to chance element, it is significant, and therefore these tests are called test of significance. We say that whether this difference is significant or not. Suppose I made a hypothesis that mean weight of the people in the town will be 60 kg, but we took some sample and in that mean weight came out to be 62 kg, then we are telling that whether it is due to randomness or it is that my hypothesis that mean weight will be 60 kg is wrong. So that means that is the whole procedure is known as testing of hypothesis or test of significance. So hypothesis testing, basically what is hypothesis? A hypothesis is a statement supposed to be true till it is proved false. It may be based on previous experience or may be derived theoretically. So first a statistician or the investigator forms a research hypothesis that an exception is to be tested. Then he derives a statement which is opposite the research hypothesis, that is denoting as H1. So the approach here is to set up an assumption that there is no contradiction between the believed result and the sample result, and that the difference therefore can be described solely to chance. Such a hypothesis is called a null hypothesis. It is the null hypothesis that is actually tested, not the research hypothesis. The object of the test is to see whether the null hypothesis should be rejected or accepted. So if the null hypothesis is rejected, it is taken as evidence in favor of the research hypothesis, which is called as the alternative hypothesis, and it is denoted by H alpha. In usual practice, we do not say that the research hypothesis has been proved, only that it has been supported. So we give example. If it is assumed that the mean of the weights of the population of a college is 50 kg, then the null hypothesis will be the mean of the population is 50 kg, that is H0 is m is equal to 50 kg. That is null hypothesis. That means my hypothesis is that mean weight of the population is 50 kg. In terms of alternative hypothesis, H alpha, that means mean is not equal to 50 kg, and another hypothesis can be mean is greater than 50 kg. Another alternative hypothesis can be that mean is less than 50 kg. So we can have different type of hypothesis. So how do we set the levels of significance? Once the null hypothesis is set up, the next job is to set the limits within which we expect the null hypothesis lies. Okay. The idea behind it is to ensure that the difference between the sample value and the hypothesis should arise due to sampling fluctuations only. If this difference does not exceed this limit, then the sample supports the null hypothesis. Like means we decide, suppose something we say 50 kg is the average weight, but if it is between 51 to 49, we may say that it is okay. That means if you got this value through sample, this may be alright and it may be due to randomness. So we have to decide the limits properly. If it exceeds this limit, the sample does not support the hypothesis and it is rejected. So now fixing the limits totally depends upon the accuracy desired. Generally the limits are fixed such that the probability that the difference will exceed the limits is 0.05 or 0.01, like that. So I can say I am setting the limits. There is only 5% chance that something due to random reasons may be out of these limits. So these levels are known as the levels of significance and are expressed as 5% or 1% levels of significance. Rejection of null hypothesis does not mean that the hypothesis is disproved. It simply means that the sample values does not support the hypothesis. Also, acceptance does not mean that the hypothesis is proved. It means simply it is being supported. So we talk about confidence limits. The limits are range within which the hypothesis should lie within the specified probabilities are called the confidence limits. are limits, it is customary to take these limits at 5% or 1% level of significance. If sample values rise between the confidence limits, the hypothesis is accepted. If it doesn't, the hypothesis is rejected at the specified level of significance. Confidence level is the complement of the level of significance. Suppose we say 5% level of significance, that means 95% confidence level. An example, suppose there is somebody wants to find that which contains more protein, whether the cow's milk or buffalo's milk. So suppose cow's milk, some samples were taken, and buffalo's milk also some samples were taken, and some values were found. Now hypothesis, null hypothesis is that difference is not significant. This difference may be due to randomness. So we find out that x1 bar, that means in cow's milk that average value is 1.92, here it is coming 2.17, and standard deviation is basically the variance. Okay, standard deviation square is this much, and standard deviation square of the second sample is this much. So we calculate one t statistics, and this is the formula, that this is x1 minus x2, that difference between the two means of the sample, under root n1, this is variance of 1, this is the variance of second, n1 s1 square plus n2 s2 square divided by n1 plus n2 minus 2, n1 is the sample size, and you put this type of data. So the t, now you get the t value if t is less than table value for t for a particular significance level, and the degree of freedom is basically taken as n1 plus n2 minus 2. This point we test. So suppose here we got by calculation t is equal to 3.6393 and degree of freedom was 10. So if we take 95% confidence level, so from the table, t table we get, that is also called the student's t table, t value we get, degree, student is not that related to student, it is basically person's name was student. Okay. So degree of freedom suppose comes out to be 10, because 6 plus 6 12 minus 2, and this comes out to be 2.23, but your difference is more than 2.23, so therefore it is difference is significant. Now in statistical process control, we do many things, like we have data figures, we have Pareto analysis, cause and effect analysis, histogram, many things. So data tables provide a systematic method for collecting or displaying data, and we can have like this, we can make the data table like defect, and we can say A, B, C. So in A, incorrect invoice, these many defects, incorrect inventory, these many defects, damage, these many defects. So like that we can evaluate. We have 3 suppliers, for each one we can make this type of data table. Then I already told about the cause and effect analysis, that is, it is called fishbone diagram. Also we analyze that what is the cause and what is the its effect. So we have divided that, suppose performance is friction in micro manufacturing. So 4 major aspects: thermal aspect, material aspect, chemical aspect, tooling aspect, and among them branches are there. Okay, that means tooling aspect, tool geometry, junction growth, many things are there. Then histogram is basically representation of data as a frequency distribution, like we say in each week minor defect and major defect and how much was the frequency. And then we talk about Pareto chart. Pareto chart is basically a specific type of histogram to identify and prioritize problem areas, like defect A occurred through maximum frequency, so it is kept here. Defect B, second most frequency, and defect C is this one. Like that we arrange in a sequence, and also we can find out cumulative percentage, that means up to this much defect. So basic Pareto analysis identifies the vital few contributors that account for most quality problem. So this is then we can have simple scatter diagram, okay, where we just talk about that, we just have some plotted experience versus performance. So we just have plotted the data in the form of a point, and we can analyze that. Okay, so now this is the data in which there is not much correlation type of thing, it is quite scattered, and we can do trend analysis, that whether it is increasing or decreasing. So, statistical method for determining the equation that best fits the data in a scatter plot, that we can do by trend analysis. Trend analysis provides forecasting to predict what is likely to occur in the future. So, this we will devote more time on this control charts later on. So, control charts focuses on the prevention of defects based on the normal distribution, and we make in control chart some upper and lower control limit, UCL and LCL. It represents this means plus and minus 3 standard deviation of the data. We say that in normal distribution theory, we know that 99.73% data will fall within plus minus 3 sigma limit. So, 99.73% of all measurements lie with 3 sigma limits. So, we make the control chart based on that assumption. Okay. Suppose this is a normal distribution, as I had said that this is normal distribution. Actually, it will never become, frequency will never become 0, it goes up to infinity, but practically it is almost 0 here. And 99.73% area of this curve is that between plus minus 3 sigma limit. So, we can make that as a control limit. That means, we can say even if it is crossing that limit, that means it is totally out of control. So, both side we can make these type of limits. Okay. So, we get so in a horizontal manner, and we say that suppose upper control limit, lower control limit, and this may be some dimension. So, it keeps fluctuating, but it should not cross UCL and LCL. We should get alerted if it happens like that. So, it is about some tool we attend. This is tool setting. So, many type of this one, this may be cyclic variation. So, finally, that I am going to tell that we also find out process capability of some plant or some machine. So, process capability is the ability to produce a product that conforms to design specification. So, process capability is equal to upper specification limit minus lower specification limit divided by 6 sigma, because it is based on that all the things are within plus minus 3 sigma, means both sides 6 sigma, within 6 sigma your most of the data falls. So, we define a index that process capability is upper specification limit minus lower specification limit divided by 6 sigma, and if process capability index is more than 1.33, then the process is well within the customer's specification requirements. So, if you see that if you want to increase, means more the CP, better it is. So, therefore, standard deviation should be less in the process. So, that is the significance of this USL minus LSL by 6 sigma. So, this I have told some basic things about statistics, and now more focused lecture will follow in the subsequent classes. Okay.